Here again, for comparison, here shows 8 columns of numbers, or 8 decimal places would be ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, and 10 millions. So the largest number that you could do in decimal with 8 places would be 99,999,999. In binary, it would be one of the ones, 2 to the first, 2 to the second, 2 to the third, fourth, fifth, sixth, seventh, or 2, 4, 8, 16, 32, 64, 128. And the largest number you could get with that is 1111111, which would be 255. That's if you added all of these together, it would be one less than whatever would be the next number. The next number, 2 to the 8th, would be 256. So the biggest number here is 255. In terms of images, if you have an image that has a 1-bit color depth, that would mean that each pixel or picture element, which is an array of bits, each picture element is 1 bit, and that means that each pixel can only be black or white. It's a 1-bit color depth, 1 bit, 0 or 1. If you have an image that is grayscale, in 8-bit color depth. Now there's also a 16-bit color depth, but it's way more shades of gray than anybody can actually perceive. So most of the work you do would probably be in 8-bit color depth per channel. Grayscale image has 1 channel, a black and white or grayscale channel, and an 8-bit color depth gives a range of from white to black of 256 steps. So 0 is black or no color, 255 is white or all color in terms of light, and different shades of gray would be different numbers. Like this one right here that you can't see because it matches my background is 128 or 50% gray. Over here in color, you may have a color image that has 8 channels, red, green, and blue, and each channel has an 8-bit color depth, so in total it's a 24-bit color depth image. And the combination of 256 possible steps in 3 channels is 16,777,216 colors. In CMYK, if you have a file that has been converted to CMYK, cyan, magenta, yellow, black, the primary printing colors for commercial printing, that would be a 32-bit color depth, or 8 bits per channel, 4 channels, and that would give you a possible 4,294,967,296 colors. That's for pixel-based or bitmap-based art. And there's a number of different file types for pixel-based images. The ones that are just 1-bit color depth, we generally call those bitmaps, although technically anything that has a map of bits or a map of pixels is considered a bitmap. But in the trade, we generally call just the ones that are only black or white a bitmap, and the ones that have other color depths, 8 colors, 24 or 32, we generally describe them by their file name, or we say they're pixel based, or it could be a JPEG or a TIFF or a number of other file formats, but all of them technically are bitmaps because it's a map or an array of bits. Finally, we do vector drawing. Vector drawing is not pixels. Vector drawing is based on mathematical formulas or vectors or Bezier curves, and I'll have another presentation for you on that before we start drawing with Bezier curves. Bezier curves are mathematical. You don't actually see them, although when drawing in Illustrator you can see a representation of where your vector curve is, but in reality that's a representation of what is purely a mathematical formula. And the only reason you see it here in my PDF is that I've applied a black stroke to the path that is defined by the vector curves, and given it a red fill. Without a red fill or a black path, you wouldn't see anything, but in drawing mode in Illustrator, you would see a black line representation of where the path actually is. This is a photograph taken in 1955, and this person is standing with 62.5 thousand IBM or Hollerith punch cards, and that equals 4.5 megabytes or 4.5 million bytes of data. Remember, there's 80 columns of holes on each one of those. Each hole can represent any of 256 possible alphanumeric characters. This grayscale image that you're looking at has an 8-bit color depth, or 0 to 255 for each bit, and the original is 6.14 inches by 8.53 inches at 300 pixels per inch. That is 4.5 megabytes of data with no compression. So if I wanted to make this picture digitally in the age of punch cards, I would need this many punch cards to represent this image. I want to talk a bit about bitmaps, halftones, and raster imaging, because this is about how we get our images into something that gets commercially printed, or actually it's also how images end up on your computer screen. A bitmap is a series of pixels in rows and columns, and this one here represents 50% gray as a 300 pixel per inch image, scan or digital image, and this is 4 pixels by 4 pixels, or here's 16 pixels of 50% gray. In order to print that commercially, it would have to become a halftone, and the raster image processor will convert this into a 150 line halftone, or it's 150 lines per inch or 150 dots per inch in the halftones, and it becomes 2 dots by 2 dots. So this has been misleading, because the dot itself is a square that makes up 4 of these squares that you see in the bitmap. But the way the screen is created at 45 degrees, it appears as a diamond here. Zoom in a little on this again. If this was a 95% gray, then everything would be white except for a little 5% area of each square. And if this was 5% black or a 5% gray, then this much would be a black dot and everything else would be white. So generally speaking, in commercial work, actually in most printing, commercial or not, you generally want the resolution of the image in the computer to be twice the pixels per inch as the halftone dots per inch in your output. So this one's 300 pixels per inch, and this is 150 line per inch output. The way it's output is through a raster image processor, and the raster image processor will take each of these dots and convert it into 10 scan lines. And again, I'm going to zoom in on this. So the raster image processor will tell the image setter or the plate burner, in order to make this image, as the laser goes across, it will be turned off and it'll be turned on a little bit, and then it's off, and then it's turned on a little bit, and then it's off again. And then each time it makes a pass, it's on a little bit wider, until when you get down to here, it's just about on all the time going across. And then the amount of time it's on is reduced, and so you would get the effect of these lines. You wouldn't really see these lines, they would run into each other and just be a square like this, but I separated them to give you a depiction of what is actually happening. So 20 lines per halftone dot at an output resolution of the image setter or plate maker of 3,000 lines per inch, which is a typical high resolution image setter these days. And the highest one I heard about, unless they've improved them some, was 3,384 lines per inch. Type is defined in the file for the font, for each font, describes the type as Bezier curves, and the Bezier curves are used to indicate to the output device, which could be your screen on your computer, which is how you see the type. The path that defines the letter is then painted in the output process. And for commercial imaging with a raster image processor, it looks something like this, where in order to do these letters, the laser is told to be off and then on for a while, and then off for a while, and then on and off, on, etc., all the way across. Because the laser has two options. It has two states. It's either on or it's off. So what does all this mean? Well, what it means is that everything we do on the computer and everything that's going on inside your computer is based on on-off signals or on-off switches. Your computer is a massive pile of on-off switches all shrunk down into a size that fits on your desktop or fits in your laptop or fits inside your phone. So you should all be able to read this now. 1 plus 1 equals 2. 2 plus 1 equals 3. 3 plus 1 equals 4 in binary. So that's bits, bytes, and binary. There is a separate presentation on electronic technology that discusses how we got from switches to things that will actually fit in your pocket.